-1. All right, hi. Welcome back to Math 234. I'm still your host, Steve Dragoo. Today we're looking at section 16.1, which will cover vector fields. Now, this video is being recorded outside of class time, so I'm just talking into the void again, so you may notice that throughout the course of the video. Also, this is the first thing that I am making after my computer's updated itself to Windows 11, and I'm now on the new version of OneNote. So you might notice that there's that bar that's absent from the top of the page telling me to update. So if I crash out at any point during this video, that'll be why. So with all that said, let's just get right into it. So some stuff that we'll want to know, and wow, yep, just right away. Somehow touch to ink got turned back on. Okay, but we're not crashing out. This is fine. We can deal with this. Everything's okay. All right. Trying again. So, vector fields. We'll look at vector fields in a couple of different ways, both in R2 and in R3. So 2D vector fields and 3D vector fields. Just a matter of how many input variables we're looking at. Just X and Y or all three of X, Y, and Z. So a quick example was just looking at the vector field f of xy gets mapped to -yx. So that these fields will be turning points into vectors. They take a point as their input and their output is a vector. And we'll draw the vector at the point that generates, we'll draw the vector at the point that generates that vector, which is what it creates a field. It's made up of a whole bunch of vectors. And again, they get generated from points. So here's a quick sketch of what this field might look like, going through a few of the points that are somewhat close to 0, 0, and still use whole numbers. Tried to sketch that out relatively nicely. I also took another crack at it over here on the right, where I just sketched out all of the vectors that would appear on the X and Y axes, and then also along the lines y equals X and y equals -X. You can sort of see that this vector field is swirling counterclockwise with its center at the origin. So all of those vectors are kind of moving in a counterclockwise direction. Uh, then a quick overview that would have been covered in the pre-class video, but looking at functions that take us between different dimensions, and the first three at least. So starting by looking at all of the functions that go to just one dimension. So starting from 1, 2, or 3 dimensions, and then going to one dimension, that sort of function is going to be a scalar function because we'll take 1, 2, or 3 input variables, but just give ourselves a number as its output. I'm trying to highlight those three in color over here. Green for one variable, blue for two variables, and then orange for three variables. So that's X or XY or X, Y, and Z all going to a scalar value. So those are scalar functions, the stuff that we kind of have already dealt with in algebra. Then the first couple of vector functions we looked at, we're taking one dimension and stepping that up into either 2 or 3. So that'll be a 2D vector or a 3D vector function. And starting from one dimension means that they only have one parameter. Usually we used t as that single parameter. Notably, that third option is a curve. Going from one dimension to 3 dimensions gives us a curve in 3D space. Again, this will be a one-dimensional object, so it is just a curved line, but it's passing through 3 space. We only need the one parameter to talk about it, that being t, but then it is represented as a vector function having x, y, and z components. Also, to just pop back up for a moment, if we had our two parameters creating a scalar function that's going to generate a surface, meaning it's just going to be the thin outer shell of some three-dimensional object. And if we're taking all 3 dimensions going down to one dimension, so taking x, y, and z and turning that into a scalar function, that'll generate a solid object for us. So some sort of 3D shape that also has a thickness to it, just as a decent way to be looking ahead at some of where this chapter is going. But then the real fun ones, the one where we actually have our vector fields, take multiple inputs and go to multiple dimensional outputs. I think the best of which to look at are going to be the 2 to 2 and the 3 to 3 vector fields. So that's primarily what we'll focus on. So starting from 2 dimensions means that we now have two parameters, x and y, or sometimes s and t if we're going with parametric functions. But a 2 to 2 vector field is going to take x and y as its input variables, and it will output vectors into space, here represented by p and q. And when we step that up to 3 dimensions, that'll be p, q, and r for each of the component functions. We'll give them those labels. Also try to stay consistent with the color scheme that I use here. So I'm typically going to be using purple for the X component, yellow for the Y component, and magenta for the Z component when I really want to call attention to those pieces. So up here, an example of a 2 to 2 vector function, so two input variables to a two-dimensional vector, was the example we looked at right at the beginning. That field, negative yx, is a 2 to 2 vector field. It's a two-dimensional vector field that takes x and y as its inputs and outputs a two-dimensional scalar. 3 dimensions down to 2 dimensions is a bit of an odd duck. So it takes all three input variables, x, y, and z, but just creates a two-dimensional vector, here represented by, some three-dimensional space, some three space over there with those orange vectors, but none of them have a z component to them. Those are all flat vectors going either left and right or forward and back. So not somewhat interesting, but not as chaotic as it can get, because ultimately the ones that we're really going to want to pay attention to are down here at the bottom, taking all three input variables, x, y, and z, and going to a three-dimensional vector. So now those vectors that we originally drew as flat can have an up and down direction to them as well. But now into the fun stuff. Just sketched out or grabbed a few example pictures from the textbook. So we'd have a few things that we can look at. But for the most part, we're going to be using vector fields to be representing either a force field or a velocity field. Two most common force fields that'll come up both in our class and also in maybe the first couple of physics classes that you might look at, is where fields have a lot of application. It'll be things like gravity or the electromagnetic force. But really any sort of force that we want to talk about, if it can be looked at as a field, so something that's acting over a large area or even a 3D space, like gravity or the electromagnetic force, we can use these vector fields to represent those forces. And as we've already looked at in the course, we actually have seen a vector field before, and that's when we did the gradient. So the gradient, which took a scalar function of x and y, or maybe x, y, and z, turns it into a vector valued output. That is going to be an example of a field. The gradient of a function will generate a field. And as it turns out, that's a rather special type of field called the gradient vector field. But more importantly, we call a field conservative if it is the result of some gradient. So if there is a scalar function and we take its gradient, and that'll give us the field that we're looking at, we'll say that that thing is conservative. We're going to introduce the definition right now as coming from, it's defined specifically as the gradient of some function, but we're not really going to focus on this until we get to section 16.3, when we look at the fundamental theorem for line integrals. So we're going to rely on these conservative vector fields a lot when we get there. So I want to introduce them now. Again, it's just some field that is the result of a gradient, and that is a rather unique property of some very special fields that will not hold all of the time. And in fact, most fields are not conservative. It takes a special set of circumstances in order to have a conservative vector field. But when we do have them, there's a certain amount of math that's going to work out rather nicely for us. So again, conservative vector field, one of the more important topics that's in this section, but we're really going to be focusing on it when we get to section 16.3. So look forward to that later on. It'll be super duper fun. Right, let's take a look at an example. And for this first one, I just want to identify the vector field in the plot to the right. And first, I want to just say that we're going to rule out none of these for right now. Let's just focus on matching the vector field to one of these four options. To say we somehow know that it already is one of these options because it happens to be a problem in a math class. And just go over some of the ways we might try to identify what this field is. So I am going to start by just looking at a couple of points. So I'm going to look at the point 1, 1. If I head over to my field, I'm looking at this vector right there, pointing up and right. Yep, if I just kind of look at what's there, I'm not going to worry too much about the numbers, just trying to get a broad sense for what the field looks like at the point 1, 1. And again, it's going up and right. And my four options, A, B, C, and D, at the point 1, 1, might look, well, will look something like the following. So A, if I plug in 1 and 1, I'm going to get 1 and 1 minus 1. Of course, with the new version of OneNote, I don't have access to my erase button anymore. Not super ideal, but I digress. At point A, I get the vector 1, 0. Similarly, if I look at B, I'll get 1 and 1 minus 1 again, which will again be 1, 0. C is going to be 1, 2. And D is also going to be 1, 2. So of these options, I'm just going to rule a couple of them out. I know that my vector needs to be pointing up and right, but both A and B point right and not up or down at all. They point flat in the vertical direction. So neither option A nor B is going to work here because I can, just by checking that one point, see that they're not going to fit very well. But the other two, I mean, there's no way to differentiate between them at the point 1, 1, so either of them work. But notice that both fields C and D are pointing right and up at the point that I wanted to call attention to. So if only those two could still work, why don't I go try and pick out another point to emphasize which of these two fields ought to be correct. And often, if I'm trying to identify a field, I think looking near the axes can be helpful a lot of the time. So in particular, I'm noticing up here near the top, my vector field is pointing nearly, and my vector field is pointing nearly straight up. Right? It's pretty close to just going up. There's not a lot of left and right movement there. So I'm going to pick a point that's near the y-axis, but also pretty far away from the x-axis, something that's kind of just near the top of my graph, and compare my two fields C and D. So it looks like a decent choice here would be the point 1, 3. Let's go do that. Look at x, y equals 1, 1, 3. Equals 1, 3. There we go. And between C and D, well, they're on screen over there to our left. C is going to field x, x plus y. So that'll be 1, 1 plus 3, which is 4. And D will be y, x plus y. So that looks like 3, and then 1 plus 3 is 4 again. So of those two options, D points a fair amount to the right, right? It's got 3 units pointed to the right with 4 up, whereas C only points 1 unit to the right with 4 up. So C looks like it's a much better choice here. Because the x component depends only on the x value, right? The x component of the field depends only on the x value. If I'm near the y-axis, I'm not going to see a ton of left or right movement, which is consistent with the field I saw over on the left. Now, a couple of other things kind of worth pointing out, because you can sort of, maybe let your eyes go a little fuzzy and notice a few patterns about the field without having to check individual points. So one of the things I might notice is that there's kind of an interesting shape happening along this line right here. In particular, looking at the field along that line, my field seems to not be moving up or down at all. If I'm looking at all of the vectors that are along this yellow line, I'm seeing mostly straight left and right vectors along that line. And I also can just write down real quick, maybe move this out of the way because I want to label the yellow line. That is the line y equals negative x. Or another way of writing that is that x plus y is equal to 0. So looking along that yellow line, I think it is suggesting that the y component of the field either is or is possibly parallel or is some component that looks a lot like x plus y equals 0. So heading back over to the fields that I had, both C and D have that property to them. So I think maybe x plus y is a decent idea here. To elaborate on that, I also want to look at one of the web work problems to kind of keep going along with the same idea of identifying fields based on some property they have. Because I can, of course, just pick individual points and go check the vectors there. But often that's, looking at individual trees and trying to decide what the forest looks like. So maybe a broader approach could be helpful. So we haven't really gotten to this part yet. So I'm going to kind of skip over the part where we need the vector fields and just say that I've already generated them over here on the left. So here are my 4 vector fields. So I'm going to be focusing on those. They were generated by the functions 1, 2, 3, and 4. But I want to match these up to the fields on the right based on some of their broad properties. So for graph A, I again see a line appearing along y equals negative x, right? And here, even along that line, I'm seeing a couple of things. One, my vectors aren't moving left or right, nor are those vectors moving up and down. In fact, I don't really see any vectors at all. I'm seeing 0 vectors along this line, which again, the line y equals negative x is the same as x plus y equals 0. So I would think that I'd see something like x plus y for both my x and y components, or both my p and q components of the field that's creating this line. And so when I look over at my options, I see that showing up in option 1. I don't exactly get x plus y, but I do have 2x plus 2y, which is, at least parallel to the set of vectors that I think I should see. So I'm thinking that because I see that x plus y property in field number 1, it's a good bet for option A. The second one that I've highlighted initially is D over here. And I'm looking at all of the vectors that are attached to the y-axis. Right? As I'm looking at vectors along the y-axis, moving up and down there, I can again see that I have flat vectors there. there's no up or down movement along those highlighted vectors there, highlighted vectors in yellow. So that suggests to me that this field along these lines has something going on for x, but along the y-axis, that's at 0. Right, my field should be 0 along the y-axis. Y-axis, of course, being the line x equals 0. So I might be looking for a field here that has an x dependency in the y component of the vector, so that q component. I'm thinking I'm going to see an x show up in that position. So looking at my available options, I think 4 is a pretty good bet for field D. So again, that x component depends only, or the y, excuse me, the y component, the up and down component of the vectors depend only on the x position, which means as I move up and down, I don't see a ton of movement up or down. I start to see the up and down movement happen as I go left and as I go right. Cool. And then for the others, option 3, field 3, 2x, 2y, all of those vectors should just be pointing outward from the origin because I just have the field. It's effectively xy. And that's what C looks like. All of those vectors are pointing away from the origin. So 3 is a pretty good bet for that one. Then the second field ends up looking a little nasty. I mean, taking that derivative, I've got a cosine and some square roots going on in there. Uh, but what I see when I look at that field is that the direction of the vector is going to oscillate because it's got a cosine in there, right? So that's going to, things are going to keep switching direction, but also it's going to be related to r. It's going to be related to the distance from the origin because I see that x squared plus y squared showing up. It's often a good substitute to use r or some kind of polar coordinate there. And I can see that with field B as well, is that there are some circular patterns showing up. So when I see circular patterns, I usually think there's got to be something with x squared plus y squared going on. And often some trig functions as well. Those both suggest circular patterns to me. So option 2 for B. But anyway, maybe I should have just done example 1.5 first, since that would have let me have a gradient to talk about. But we've looked at gradients before. So if I want the gradient field, that really just means calculate the gradient. So that gradient field, we'll call the field capital F with a vector hat on it. It's just the gradient of my scalar function, and it looks like the following. First, I need an x partial. So I think this is 2y plus 3 plus y e to the negative xy. That's my x component, or often p. I'll write that in because we will be using the PQR notation quite a bit in the coming sections. Now, for the y component of the gradient field, I just need the y partial derivative, which looks like 2x plus x e to the negative xy. That'll be the y component, or q is often what we'll call that part. And then also notice the derivative of 3x, or the partial derivative of 3x with respect to y, is 0, because that has no y dependency. All right, and then in our next example, we want to sketch out a few level curves, calculate a gradient, and then compare it to a couple of points that are on that graph. So right off the bat, I want to look at the function x squared over 4 plus y squared over 9. at a few values for k. 1, 2, and 4 were suggested, but I'm actually going to change that. I want to look at 1, 4, and 9. Uh, just to make some of my math easier, I'm going to look at square numbers for the level curves because it'll work nicely when I want to actually find uh, find the values here. So what do I want to do here? I've got my field or my function. It's x squared plus y, x squared over 4 plus y squared over 9. And if I'm looking at level curves, I've really got the equation x squared over 4 plus y squared over 9 is equal to k, which in turn is going to be x squared over 4k plus y squared over 9k. And that's equal to 1. I'll just divide the 1 over. Since often when we looked at ellipses, we wanted to have their equation set equal to 1. That way the denominator of my two square terms, x squared over something plus y squared over something, those denominators will give me the semi-minor and semi-major axes of the ellipse. So if I were to just label those real quick, R1 is going to be 2 times the square root of k, and R2 being the y axis, the y, sort of like the y radius, it's going to be 3 times the square root of k. And now you might see the motivation for picking 1, 4, and 9 instead of 1, 2, and 4 for my level curve values. So let's get to calculating some of this stuff. In particular, let's go k equals 1. Mark that guy in purple. That'll give us x squared over 4 plus y squared over 9 equals 1. And my two axes are pretty straightforward. They are 2 and 3. So I'll go over and try to draw an ellipse. It's roughly that shape. Center it slightly. Cool. Right about that. For my next level curve, I'll set k equal to 4, and that'll give me the equation x squared over 16 plus y squared over 36 equals 1. And look at my my semi-major and my semi-minor axes. This time they'll be 4 and 6. And again, go over and draw that shape in. Yeah. Let's try that one more time. Close enough. And we'll get the third shape, the third level curve where k is equal to 9. That'll give me x squared over, let's see, 4 times 9 is 36, plus y squared over 9 times 9 is 81, still equal to 1. And I can see now that my two axes, my x-axis will be 6, or my x-radius will be 6, and my y-radius 9. Again, good enough. So with that said, I want to get a bit of a sense for what the gradient field is going to be looking like here. So let's go calculate a gradient. And the gradient field doesn't look too bad for this function. Looks like it's 2x over 4 and 2y over 9. And I'll go grab the field at a few points. Let's look at the gradient field at, how about 2, 0, 0, 6, and negative 6, 0. So those points would be here along the purple level curve, up here along the, what is that, the green level curve. And okay, maybe I really do need to fix that green one because it's nowhere near the point that I wanted it to be. Eh, whatever, just pretend. The third point's right there. That's at negative 6, 0. Again, it'll be a little sloppy, but that's fine. So might as well go back over here and highlight where these points are coming from. That guy's on the purple line. 0, 6 is along the blue line. And negative 6, 0 is along the green line. And if I get my gradient vectors at each of those spots, 2 times 2 over 4 is 1, and 0 is 0. 0 for the x component in the blue one, and then 12 over 9. I'll simplify that to 4/3. And for negative 6, 0, looks like negative 12 over 4 or negative 3, 0. And then draw in those vectors. They should look something about like that. So the vector field at each of these points is going outward. Right, so if I'm trying to get a sense for how this function is changing, it looks like it is smoothing out as it goes, all of those level curves radiating outward. Also, each of these level curves should be coming up the z-axis since k is increasing each time. So that green ellipse, that green level curve would be the one closest to us if we're looking from the top down, and then blue and then purple as they're sort of honing in on their center of 0, 0. Well, let's try that stuff again. I've got a new function, this time y over x plus y. Note that x is not equal to negative y. It's going to be one of our restrictions. And we'll just keep the level curves provided to us here, 1/2, 3/4, and 2. So I want to do the same thing. I'm going to take my equation, take my function. This is y over x plus y. Set it equal to k. And just kind of solve this thing so it gets into a form that I can work with, something that I recognize. You might notice that this is y equals, let's try and line our equal signs up. This will be kx plus ky. And then reorganize that just so it looks like the equation of a single line. This is k over 1 minus k times x. Again, I'll just keep tracking that k as it gets transformed. So I'm looking at a bunch of lines, in particular lines of varying slopes, but that all pass through the origin. Now, first thing I want to talk about real quick, back up to the explanation of the problem. I was told specifically x cannot be equal to negative y. And if we look at the function, I think it becomes pretty clear why we can't do that. Dividing by 0 is always bad. We don't want to do that. But if we take any point that's along the line, x equals negative y or y equals negative x, our denominator is going to be 0. So we can't look at level curves along that line because, again, function won't be defined there. So I'm going to start by just drawing in that line. So I'm going to start by just drawing in that line and saying we don't want to be along it. Maybe I'll move it slightly so that it actually passes through the origin. Kind of felt like the computer was taking over, so it must have auto-corrected to a 45-degree angle. So that gray line is y equals negative x. And specifically, we know that y cannot be negative x. So we'll cut it out. I said we'll cut it out. Good enough. So we'll kind of structure our level curves around that line. But since we solved an equation to give our level curves in terms of k right away, means that solving for these will be pretty straightforward. Our first option was that k equals 1/2. So if I look at the slope I get, if k is 1/2, I'll get 1/2 divided by 1 minus 1/2, which I'm pretty sure is 1/2 over 1/2 or just 1. So we get the equation y equals x. For k equals 3/4, let's mark this one in blue. Again, I just need the slope of the line that I'm going to get. I'll get 3/4 divided by 1 minus 3/4, or 3/4 divided by 1/4. 3/4 times 4/1, that's just 3. So y equals 3x. And lastly, k equals 2. What color was next? I think green is the next color we were going to use. If k is 2, well, then I'm going to get 2 over 1 minus 2. So y equals 2 over negative 1. Call that negative 2x. So let's go draw those points in, or those graphs in. First off, y equals x. Something about here, and I'm going to adjust some of these so that they actually do pass through the origin. It's a little sloppy in the last graph, but can't do it on this one. They've got to at least go through the origin. For the blue line, it's got a slope of 3. So how about I just start at 1, 3, bring that down to the origin. Looks about like that. If I line it up so it's along the origin and then just make it a little bit bigger. There we go. Decent looking graph with a slope of 3. And then the last one, y equals negative 2. Well, same thing. Let's just go from, let's see, negative 2, 4 is about here. Draw it to the origin. Yeah, about like that. And then I'll extend it so it actually comes through to the bottom. Hopefully that looks like it's at about a slope of negative 2. And we should pick some points to look at our gradient at. So I'll go with some relatively easy ones. How about 1, 1, 1, 3, which is, maybe that wasn't the greatest graph in the world, but again, that'll be fine. And 1, negative 2. We'll look at those points roughly there. Again, this is just a quick sketch, so it'll be all right if it's not quite to scale. Oh, but right, I should actually go calculate the gradient first, because I'm going to end up wanting that. So how about I slide these level curve calculations out of the way, put them over there to the upper right, and I'll use this lower area to calculate a gradient. So my gradient, the gradient of f, which again, this will be some field. But for now, we're just focusing on it being a gradient. I need some derivatives. Specifically, I need derivatives of y over x plus y. Well, if I'm just doing an x derivative, not much to it here. It looks like it's going to be negative y over x plus y squared. Not a ton going on there. I can just use the power rule to do its derivative. Well, the power rule and the chain rule. But the next one, I'll actually want the quotient rule for. So let's do that. Quotient rule is giraffes forgo. So G, keep it the same. X plus Y, giraffes. So take the derivative of F, which is just 1. minus forego, take F, leave it the same. Second half of forego, G, take the derivative of it, which is 1, and divide the whole thing by the denominator squared. So x plus y squared. And I get that field, and that didn't at all match the size of my previous text. So maybe let's scale it down just a little bit. It doesn't look too horrendous. Cool. So there's my vector field, but I should clean it up a little bit. First thing I'm going to do is just, I don't really want to, yeah, fine, there we go. I don't really want an arrow in my denominator. I'm going to pull out a 1 over x plus y squared, since both terms have it. That way I can just focus on the parts that are changing in the middle, which looks like it's going to be negative y for the x component. And for the y component, looks like x plus y minus y, which is just x in its numerator. To maybe keep this going with what I wanted to say about taking those gradients and keeping the P and Q components alive. P for purple, Q for yellow. Doesn't quite work. Ah, well. But again, we'll be using P and Q quite often to represent the X and Y components of fields. So I just want to keep introducing that every spot I can. But with that figured out, I should be able to go calculate some gradient values at points. So I said I want to do 1, 1, 1, 3, and 1, negative 2. So each of those are just a single step along the direction of the slope. 1, 1 is on that purple line. 1, 3 is on the blue line. 1, negative 2, we said 1, negative 2 is on the green line. And go figure out what those gradient vectors ought to look like. Well, at 1, 1, looks like it's just negative 1, 1, divided by 1 plus 1 squared, which is 4. For the blue line, well, it looks like this is going to be negative 3, 1, divided by those two things added and then squared. So 3 plus 1 is 4, squared is 16. And for 1, negative 2, well, now negative 2 will be a number, but I can't write it down because my electronic pen has run out of ink. I've told myself several times I'm not going to crash out in the middle of this video. And no good, I'm not going to have to. It came back. I love that for me. Okay. So, right, we were in the middle of getting this vector. So negative 2 is positive 2. Our y component is x, so that's 1. And divided by 1 minus 2 is negative 1, squared is 1. So if I go put these vectors on the graph, and I'll be exaggerating them for effect, the green one, the lower right, it's going to point right and up, and it's only being divided by 1, so it'll be a relatively long vector. The blue one looks like it's going to be pointing left and up, but also is divided by 16, so it's pretty short. So I'll try and draw that fairly short, relatively short compared to the others. For the purple one, negative 1, 1, be pointing left and up, and kind of in the middle of the two as far as its magnitude goes. Maybe something about like that. Honestly, I should probably squish this guy down a little bit. He should be pretty short. He doesn't have a ton of magnitude there. So those are those gradient vectors, all marked off in orange. And lastly, just some intuition on how points would move through fields. So in each of the next three cases, we're going to look at these lines, uh, well, the line segments PQ, and we're going to be going from P to Q each time. So from P to Q, from P to Q. And just looking at the fields, I want to try to figure out, is the field helping this motion happen, or is it hindering the motion that's trying to happen? So maybe I should set the stage a little better than that. Let's imagine that I've got, you know, PQ is going to be some like steel rod or something. Uh, it cannot move. It is fixed in place. And along that rod, I'm going to have some kind of a bead. So something that is stuck to the rod, it can only move along P and Q. And our goal is going to be to push that object or push that bead from P to Q. And again, it's got to stay along this steel rod. So again, sort of emphasizing that the rod, the line segment PQ cannot move. I'm going to have some object that's going to move along, some object that's going to be moving along that rod. That was actually maybe not my best color choice because I'm about to use blue for the fields. So let me pick a different color. How about orange? We can use orange, right? I'm moving from P to Q. That's the direction I want to be going. Oh, and it looks like the AI decided it wanted to add an extra set of arrows for like no reason. From P to Q, we really don't want those there. Cool. We've got to be going in that direction. So I'm going to erase that again one more time because I want to look at that again at the end. For now, let's just look at what the field is doing. If I look up by Q, my field is all pointing down and right. If I look by P, field is all pointing up and right. If I look in the middle, it looks like it's just pointing straight right. And in fact, looking at the field all the way around, all of these vectors appear to be pointing into the origin. Everything's collecting itself in there. So I'm looking at moving along this line from P to Q. Well, that's trying to go up while all the motion is directed in. So I think overall, this field isn't really helping my bead move along the chain or stopping it from moving along that rod. In fact, if I look at the field, it looks like it would probably try to center it along the x-axis. That's kind of the result of where all of those forces are going. So maybe another way of pointing that out is that it's going to be helping the bead move from P up to the x-axis, but then it's going to be hindering the bead as it moves from the x-axis up. So I think for this one, it's not really helping or hurting. Overall, I think that the forces there are going to sum up to zero. So again, maybe be thinking about the field as a force field, or maybe this is maybe all those vectors are representing the flow of water. Maybe my steel beam is like stuck in water, and this is where all that water is flowing. So in the end, the water in that field, the water in this pool, isn't helping or hurting the bead move at all because ultimately it's going to sum to zero, is my argument there. We try that again, but looking at this other field. Well, if I just kind of broadly look at the way that my arrows are pointing, this field is swirling counterclockwise, right? All of my fields seem to be going around like that. And maybe let me mark that off in blue because I'm going to be using that to represent the field. It's not a very good looking circle, was it? Yeah, well, that'll be fine. Kind of looks like my water is maybe swirling around a drain here. Okay, like it erased finally. Cool. So I've got this sort of swirling counterclockwise field. So if I just kind of look at the field along this rod over here, it's moving down and left by Q. It's moving down and right. It's moving down and right by P. And through the middle, I think it's just going straight down. So generally looking along my rod, while there is some left and right motion, looks like it's ultimately going to balance itself out. And the direction that's really staying consistent along that field is down. However, we kind of want to be going up because we want to be going from P to Q. So the whole way through, this field is hindering the motion of that bead along the steel rod or whatever, object we might want to claim it is. Let's just keep working with the bead on a steel rod idea. So since this field is it's getting in the way, it's hindering the motion, I'm going to say it's making it harder for the particles to move from P to Q. And if we've looked at an example that came out to B and C, and there's a third example, better look at one where it's going to help the field along, or the field's going to help the bead along. This one, kind of got some interesting stuff going on. Broadly, it looks like the field is moving out from the origin, but it's also got some counterclockwise spin to it as well. So it's a bit out, it's a bit counterclockwise. So maybe let's just start looking near our points, near our steel beam. At P, looks like the field is mostly just moving right. Near Q, or at least near the top of Q, it's mostly just kind of going up. If I look a little bit to the left of Q, it's also going left and up. Fine. It's also going left and up. Where in the middle, it's kind of moving right and up. But as we go, it seems like it's moving more and more up. It's kind of the trajectory of this field. And fortunately, this time, we wanted our particle to move from P to Q, which was in the up direction. So overall, I think this field is helping the particle move. It's helping the bead move along this chain. Not a ton near P itself, because it's mostly just trying to push it to the right, but our bead can't go to the right because it's stuck on that steel rod. But the further up along the rod we go, the more and more the water, and the more and more the field is pushing that particle upward. So I'd say A. Field's helping the particle this time. And that's the end of section 16.1. Uh, I'm sure I'll talk about this a little bit in class when I introduce 16.2. But the idea here is that 16.2 is going to have a lot going on, and it'll be easier if we just kind of gone over some of these vector fields first. Well, anyway, that's it for me. Okay, bye, 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 bye. Oh, and I did just remember that I wanted to show off another part of my notes real quick. Uh, Sometimes some of the sketches I do in the live version of the notes end up being not that clean. But I do have another section where I spend a bit more effort making sure that pictures are drawn a bit more to scale, and some of my handwriting's cleaner, or even the color coding will work better. So the live streams tab, if you look over to the left side of the screen, live streams, that's where I do everything in class. Whenever I record a video, it's one of the pages that's over here, but I do have a complete version, or at least a slowly becoming complete version of the notes, just under the Fall 25 notes section. Or if you're watching this video sometime outside of Fall 25, I'm sure it'll be the one that's in purple, but might have a slightly different name. I'm sure it'll be at the top of my notes tab. But anyway, I digress. If you check over here, I've got each section worked out in a somewhat clean manner. So if I were to go back and say, look at the example where those ellipses were, I spent a lot more time and effort trying to actually make sure that those things were centered and roughly to scale. And same with the lines over here, kind of the same thing. And actually, I think that we did pretty well with drawing the fields. I was pretty happy with how that came out. But anyway, if you ever want to, you know, check that out, or if you're trying to just look at the written version of the notes instead of following along with the videos, because maybe just referencing something written in the notes will be faster than scrubbing through a video. Uh, Here's where it is. Yeah, might have led with that for the video, but said it's here at the end. Okay, bye for real. Bye, 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 bye.